All right, we're live here. So yeah, welcome. End of the first week. So we're making progress. Should have my screen up. I should have audio and all kinds of good stuff going on. Can anybody see my... Oh, there we go. How's that? All right, we have the technology. So yeah, yesterday's video recording, I was recording the wrong window for whatever reason. So no videos from yesterday, but we're going to go over linked lists again today, basically from start to finish. So, hopefully you were in class yesterday and heard, and played along. But let's go through linked lists again really quickly here, kind of the whole story, and then let's just jump into programming assignment 1, which is all about linked lists. So that's really where we're going to talk about these data structures and get most of our exposure to them. Any questions on the ODP, first of all? So the ODP doesn't really deal with linked lists, and I know we had some code yesterday that got lost in the video, but it looked like a number of people had succeeded with the assignment anyway. So any remaining questions on the one-day program, which is due tomorrow morning instead of this morning? Again, just make sure the fields of the structure are in the exact order that's specified, and make sure you do, initialize element 0 as defined, and then elements 1 through 99 inclusive, initialize those as defined, and you should be good to go. Testing in the main program is there's no specific answer to that, but basically, I think an easy way is to use GDB, because GDB you can say, print data bracket 0 and see exactly what the fields are, print data bracket 99, see what the fields are. But you could write a for loop, you could get fancy and have an interactive program that asks you for an index and prints out the value of the fields at that index, right? Easiest way may be to either use GDB or just write a for loop that just prints out all 100 elements from your array. Hey, someone had success, good. Oh, but it wouldn't work with your own test function. Well, that's interesting. Usually it's the opposite problem. So when you write your own test function, so make sure that if you're writing your own test bed, that you're actually allocating space. Like that. And then initialize it with a call to your init function. Right, and then you should be able to print out data bracket, anything from 0 to 100 dot, and the name of the field you want to print, data validator next. But make sure you do this. If in your main program you said struct node star data, that'll definitely segfault when you try to use that array. Yeah, my first guess would be uninitialized array, and that would blow up when you called init, because init assumes that the memory exists. All right, so let's do a quick overview of linked lists from the top, without worrying again about the motivation behind this and the justification for these things, which we've been talking about for a few days. So let's just look at kind of the mechanics of a linked list. And there's sort of two main ways to do this. Let me start with the picture version, okay? Because that's the thing that's probably missing most from the missing videos. So let's suppose that we have a list that contains prime numbers, so 2, 3, 5, 7, and 11. So the way that we store this is by making these structures that contain two pieces of information. So they contain the number itself that we're trying to store, but they also contain a pointer to the next thing in the list. So this 2 points over here, the 3 points there, the 5 points here, the 7 points here. And where does the 11 point? Well, since it's the end of the list, there's nowhere for it to point. So we record this as what we're going to call null. Okay, and it's a special value that when we see this value, we know it's not a pointer to another node. It's basically an illegal memory address, and it's usually 0. So this is a representation of a list containing these 5 numbers. And the motivation for doing this is that suppose we want to insert a 4, right? Well, we can simply find somewhere in memory where there's space to store a new number. We can put a 4 in there. And instead of moving everything in an array down, we only have to make 2 changes, right? Basically, we need this 4 to point to the thing that comes after it, and we need the thing before it to point to the 4. So we'll change this one field on this node, this 3, to point down here, and then we'll change the 4 to point to the 5. And even though, in memory this 4 is nowhere near where it should be, it doesn't matter, because we're not looking at, these things sequentially in memory. We're basically starting here and we're following these links. And so the 3 is followed by 4, which is followed by 5, which is followed by 7, which is followed by 11, which is the end of the list. So that's sort of the visual description of a linked list, right? It's these things that we call nodes. So let me put a key down here. So this is a node, and we think of it as having 2 fields. I'll just call this field data, and that's going to have the actual number or character or string or whatever that makes up our list, and it's going to have another field that we call next. And next is somehow a reference to the next node. So our list is this chain of nodes where each node points to the one that comes after it. And then if we want to delete a node, if we decide we don't want 7 to be a prime anymore, so we're going to go Pluto on it, and we want to take 7 out of the list, what do? Well, we take the node before it, which was 5, and instead of having 5 point to 7, we'll have it point to the node after 7. And we've just removed 7 from the list. All right, so that's an add operation. That's a delete operation. Searching is very straightforward. If you want to know, is there a 4 on my list? Well, start with the first node. That's not a 4. That's not a 4. Hey, there's a 4. If you want to know if there's a 6 in the list, that's not a 6. 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 Hey, there's no 6 in the list. Yeah, poor Pluto. All right. So we can add, we can delete, we can search. Now if I wanted to add a 6, right, instead of making a new box and putting a 6 in it, ideally what I would do is I would say, hey, you know, this box right here, it's not being used. There's nothing pointing to it. So I could change this to a 6, I could change it to a 10 million, I could do anything I want with this. It's not going to hurt my list. So if I want to add a 6, right, I would reuse this box, change that to a 6. And how do I put it into the list? Well, it should come after the 5, so I want the 5 to point to this, and then I want this to point to whatever the 5 points to. So while I'd end up, you know, restoring the old link that I had, that's just coincidence that that happened. But, you know, if it didn't happen to come right after the 5, I would still, you know, insert it wherever. All right, and then there was one more detail we ended with, which was this question of suppose I wanted to delete the 2. Or suppose I wanted to insert something before the 2. I've been using the upper left corner of my paper as the starting point for my list. And even though, you know, these other nodes end up wherever, right, each time that I've gone through the list to search for something or whatever, I've started right here. Well, suppose I delete a 2. Really what I need to do now is when I work with my list, I need to suddenly start here. Well, how do I know that this is where my list starts? So I need some other piece of information. And so I described something that we call a sentinel node. And a sentinel node looks like any other node, except we don't do anything with the data piece. And this next field points to the first node in the list. So we do exactly the same operation that we've been describing for add, for search, for delete, except we don't actually look at the data field of the sentinel node. It's really just a pointer to the beginning of the list. But everything else is exactly the same. So now if I want to delete the 2, what do? Well, I take the node before it, which is the sentinel, and I change its point to the node after. So I change the sentinel pointer to go right here, and I've deleted the 2. And if instead of deleting the 2, I wanted to insert another node, so let's say I want to insert, you know, a negative 17, because that sounds prime to me. Well, it should go before the 2. So what do? You take the node that comes right before where you want to insert it, and have that point to your new node. And then you set your new node to point to what that prior node used to point to. And we've still got a good linked list. Start from the sentinel. First node is negative 17. That's followed by a 2, which is followed by 3, which is followed by 4, which is followed by 5, and then 6, and then 11, and that's the end of the list. All right, so that's how a linked list plays out in pictures. All right, and when we're doing any data structure programming in this course, I want you to always try to have in your head some kind of picture of what you want your code to do. Don't just sit down and open an editor and start writing code. Make sure you know what you want your code to do before you start writing it. Otherwise, you know, you're writing code, you get 50 lines in, 100 lines in, and all of a sudden it's like, what am I trying to do? And you've written a bunch of code, but you have no idea what it's for. You got to know what your goal is and how you're going to accomplish that goal before you code up a computer program, which basically tells the computer, you know, how to do this thing you want done. So yeah, this is a good chance to get better at pseudocode. And you can write pseudocode any way you want. You don't even have to write code. Right? I mean, this is pseudocode in some sense, right? I could describe, you know, the process of inserting a node just with pictures. But you gotta, and you know, a lot of times it ends up just being C, which is fine. It's C, but we don't need semicolons. But you want to make sure you know what the program's behavior should be. Not just, you know, I want it to delete a node, but what steps will it take? Because if your code doesn't work the first time, you want to be able to run through it in the debugger and see exactly what's happening at each step and compare it to what you think should be happening. Well, I should start at the sentinel, I should move here, I should move here. When I get here, I should realize that this is bigger than the number I want to insert. And you can step through in the debugger and see if that's what actually happened. And if in the debugger you go all the way to here, you know you've got a problem in your logic. And so you go back and you look at how you coded things up. So we're always going to draw pictures and come back to those. All right, so to talk about how we actually implement this in code, let's just jump into programming assignment 1. And we'll use that as our specific example, which will be fortuitous because then we'll have something we can use. So I'm going to switch over to another window. All right. So, programming assignment 1, you're going to create a linked list, and we're going to do it by using an array of structures. Okay, so ODP202 was a build-up to this. So we're going to use a struct node, which looks just like 202. It's going to have a data valid and next field. Data next valid. Okay, data is an integer. That's the number that we're storing in our list. So this whole program is creating a linked list of integers. So data is the actual number. Next is also a number, which is an index in the array. It's the location of the next node in the list. And we're going to use element 0 as our sentinel, so our data is never going to get stored at index 0. So anytime we see a 0 in this next field, we're going to take that as a flag. And if next is 0, we're going to say that means the end of the list. And then valid is going to be a flag which tells us whether or not that location in the array contains a node. So, you know, on a piece of paper it's easy. If I draw a box, it's you know, a valid node. If I delete a node, I could erase that box, right? And then we could just look and see, you know, where the nodes are. In the memory of a computer, right, every location in the computer's memory has values in it. Any location in our array of nodes will have a data field and a next field. And there's no way to know if the value that we're seeing in there is part of a list or not. And so when we want to create a new entry for our list and we need to find a space in our array to add this new node, how do we know if a space is being used or not? So rather than, you know, starting at the beginning of the list and seeing if we ever encounter that index in the array, we add this third field, which is a valid flag. And every node has a valid field, and it's 1 if the node is in use and 0 if it's not. If it's 0, it means the node has either never been used or it's been deleted. So when we delete a node, we have to do two things. We have to remove it from the list by having the previous node point to the next node, but then we also have to set the valid flag to 0, so that we know that this entry is available for use. Alright, I don't want you to hardwire the 0 when you're looking for this end of list. Okay, for the valid flag, just use a 1 or a 0. But for looking at the end of list, I want you to use a variable, a symbol called myNull. Okay, so whenever you want to know, you know, is the dot next field equal to 0, see if it's equal to myNull. Don't compare it to 0. I'm going to insist that you use this symbol. And the reason why is because of PA2. Alright, your main program will be a struct node of 100, an array of 100 struct nodes. Okay, just like the ODP, which means it can hold up to 99 data nodes in your linked list, and list bracket 0 is going to be the sentinel. Alright, so you've got the whole setup done once you're done with ODP 202. You've got the basic structure for, you know, the beginning of an empty linked list. Other than the numbers that I asked you to use to initialize in ODP 202, those numbers are totally bogus. Okay, that was just to exercise your initialization code. But the structure of the array, the idea that 0 is different from the others, right? That's all PA1. All right, so let's take a look at this array in memory. Just as an example. So here's data, here's next, here's valid. All right, so I want you to write an initialize function, which takes an array of struct nodes and sets some values in there. Okay, this is basically ODP202, except like I say, the values you're using in ODP202 are bogus. The values in this initialize function are meaningful. Okay, how do we create an empty linked list? An empty list has a sentinel node and no other nodes in the array. So how do we set that up? Empty list has a sentinel node at index 0 pointing to my null. All right, so so this next field should be my null. I would go ahead and mark that valid, although this is a special case, right? This sentinel node. So you can choose to use or ignore the valid field, but set the next field equal to my null, and then the valid flag in all other nodes should be cleared. So all of these nodes set the valid field to 0. So that if you look at this data, you know that none of these things are in use, and you know that your sentinel node points to my null, the list is empty. So your init function, same as ODP202, but set up these values instead of the ones from 202. All right, and then I want functions that will let you add a number to the linked list, print out the elements of the linked list, delete a number from the linked list, and search for a number in the linked list. Okay, so you're going to implement those 4 functions, and we'll go through pseudocode in a bit to see how to actually do some of these things with the array. But you're basically going to do what we were doing with the pictures, but by manipulating elements of this array. So in addition to initializing, you want to be able to add, print, delete, and search. And each of these takes, you know, the array itself and a number to delete, a number to search for, a number to insert. The print function just takes the linked list, and it prints out all the nodes. And since you're inserting things in order, when you print, all you really have to do is go through your list from beginning to end, print out each node, it should be sorted. Okay, your list is always sorted internally. So we'll do pseudocode in a few minutes. Let me introduce a concept, if you haven't seen this before, concept of an abstract data type. So we're going to talk about data structures a lot this quarter and next quarter. And we're going to talk about linked lists for a few weeks. And we've described linked lists a number of ways. And we've seen, you know, pictures for showing and manipulating linked lists. And right now we're seeing, you know, the start of how we can build a linked list using an array of struct nodes, right? But there's a number of ways to think about a linked list. We can think of it in terms of, you know, how is memory being manipulated? Where is this new node going to be stored? That's a very low level, sort of close to the metal way to think of a linked list. We can think of it from a higher level in terms of, you know, when we want to add a node, we're going to find a new spot we can store it. We're going to stick the node in there. We're going to adjust the previous node, and so on. That's a higher level. There's a higher level still, the level of sort of pure abstraction, where we don't care how you make the linked list work. And this is the level that we call an abstract data type. So if we think of a linked list as an abstract data type, it's really just this sort of magical structure that lets us initialize the list, add things, remove things, search for things, print things. And as somebody who's writing a main program, that's the only thing you care about with a linked list. How do I interface with it? You don't care if it's implemented with arrays. You don't care if it's implemented using pointers. You don't care if there's a sentinel node, right? Those are implementation details. As a higher level programmer, all we care about is these 5 functions: initialize, insert, print, remove, and search. And we want the idea that when we insert, it's going to insert it in the spot that it belongs so that the numbers before are smaller, the number after is bigger. And when we print, it's going to print the nodes out in order. But when we're in 223 and we implement a linked list, we're not going to know anything about how that list is actually implemented in terms of, the computer's operations. Is it using pointers? Is it using an array? Does it have a sentinel node? Does it have backwards pointers? Is it stored, in forward order or backward order? We're not going to know any of those things, and we're not going to care about any of those things. It could be that, when I call my add function, it sends a text message to a friend over in Portland in a coffee shop, and this friend, pulls out their pen and paper, and they write the new number that's being inserted in between the numbers that are bigger and smaller. And it could be that when you say search, it sends a text message, and my friend pulls out their piece of paper and looks to see if they have the number, and they text back either a 1 or a 0. And then your code returns that as the value of the search function. Perfectly legitimate way to implement a linked list. And your main program should be completely agnostic to how the list is implemented. Okay, that's the theory of an abstract data type. We'll come back to this again and again. But while you're writing your main program for PA1, I want you to try to have this firewall between your main program and these lower level details. Right? So your main program should never, monkey with the valid flags or the next fields or the data fields or anything like that about your linked list. Your main program's whole interface to the linked list is through these 5 functions: initialize, add, print, delete, and search. Okay, so that's what abstract data types are about. And the more we work with this stuff and the more we write code using these ideas, the more clear these ideas will become. So if they're sounding kind of fuzzy right now, that's okay. All right, let's talk about your main program, then we'll go back and we'll talk about details on these functions. Your main program is basically a command line interface to the user. We're going to see this a lot this quarter. So you run the program, right? Linked list, whatever it's called. You run your program, and it can, print out a brief message in the beginning if you want. Don't clear the screen or print War and Peace or anything, but you can say, welcome to my program, and then print a prompt. So greater than sign, and wait for the user to type in a command. And the user basically will type in a command, and that command will do something with the linked list. And yeah, linked list is abbreviated LL in this assignment. All right, so a limited set of commands. The user can say I followed by an integer, and this should insert the integer into the list. And you should only allow a number to be in the list once. So before you insert the number 5, check to see if 5 is already in the list. If it is, then print out the message node already in list. Otherwise, try to insert the 5. If you succeed, print out the word success. If you don't succeed, print out the words out of space. And the only way you can fail to insert a number into your list is the number's already in there or there's no space left. Alright, if the command the user types in is P, that should print out the numbers from the list on one line separated by spaces. If the user says S followed by a number, then it should print out either found or not found. If they say D followed by a number, it should either say success because it deleted it, or node not found if that number is not in the list. If they type an X, the program should exit. If they type anything else, you should give them a help message showing a synopsis of these commands. And then, assuming they didn't exit, go back, print another prompt, wait for another command, and just keep doing this. And I want you to try to stick to this behavior as closely as possible. When you're developing and you're debugging, you can put in extra print messages, you can put in extra spaces, you can change the wording of things. The version you submit for grading, I want it to be as close to this as you possibly can. Right? Prompt is a single greater than sign followed by a space if you like. I will print out one of these messages, node already in list, out of space, or success, and so on and so forth. Do we need to parse user input? Well, you need to understand if they typed I followed by a number, or P or S followed by a number, and so on. So you need to do some parsing there. And if they say I and it's not followed by a legal integer, print out a synopsis of legal commands. If they say D and it's not followed by a number, or they say D and it's followed by ha ha ha, that's not, you know, one of these commands. Print out a synopsis of legal commands. Yep, so you get to bring out old scanf with fgets, which is good stuff. All right, let's go back and look at the details. You can read deliverables and grading, and we'll go through those later, but those don't affect how you get started on this. So let's go back and look at some details on these actual functions and see how these things would manipulate the array. You can write a generalized parse function and you know, perhaps not have to keep writing one. Or you can get really good at writing them because you've written them so many times. I guess it depends where you want to spend your energy. But I mean, scanf is already, in some sense, a generalized parse function that lets you specify, you know, what kind of parsing you want done. But yeah, a lot of our assignments will kind of look like this, where we're entering these really short 1 or 2 letter commands, followed by optional arguments. Alright, so let's think about some code. So we already know about init, right? That's ODP. The add function is actually probably the trickiest function of all of this. So let's talk about the add function. And you're going to pass it the array of nodes, and you're going to pass it an integer. Okay? And I'm going to assume that before the add function is called, the main program has checked to make sure that the number's not already in the list. So in your main program, if the person says add the number 12, first thing your main program should do is search for 12. And if it finds it, you can say, you know, that number's already in the list. If it doesn't find it, now we can call our add function with 12. Alright, so let's see what our list might look like if we had some data in here already. So suppose our list had the numbers 10, 15, and 25. So it might look like this. Alright, so there's a 10, 15, and 25. These 3 spots would be valid. The sentinel would point to index 1, index 1 points to 2, 2 to 3, and 3 says the next node is my null. So that's the end of the list. And now suppose the user says insert 20. Alright, let's go through this. I'm not going to write this out, but let's go through this and think about it in terms of steps that the computer could do, right? Because you and I mean, we can just look and say, oh yeah, just put a 20 here. But let's think about this in terms of steps that a computer would be capable of. So we're always going to start with index 0. That's the sentinel node. And we're going to look at its next field. Okay, we're not going to look at the data field. We're going to start with next. And we're going to say, okay, that's index 1. So let's look at index 1. Let's look at its data value. Its data value is a 10. That's smaller than 20. So we want to insert somewhere after index 1. So I'm going to keep track of where I am. So I look at index 1, okay, and that's a 10, and that's too small. So I know I want to look at the next node. So I look at the next field, and it tells me that's going to be index 2. Okay, so I'm going to remember where I was a moment ago. My last index was 1, and I'm going to switch to index 2. All right, I'm going to check the data value of index 2. That's a 15. That's also too small. So I want to move forward to the next node. So I'm going to remember that my last index was a 2, and the index I'm going to is a 3. All right, now I get to index 3 and I look at the data value, that's 25. That's too big. All right, so what have I done? I started at the beginning of the list. I moved through the list and I kept track of the last index and the current index until I got to a node where this index's data value was bigger than what I want to insert. At this point, I want to insert between the node at last index and the node at this index. All right, so let's play this out in pictures before we write some C. So here's the sentinel node. That points to a 10, there's a 15, there's a 20. That points there, that points there, this is my null. And I wanted to move through here and find the spot where, sorry, this is 25. Find the spot where the 20 should go. I'm using a pair of pointers. All right. And this is the most important part about coding linked lists like this. You want a pair of pointers. The reason is we can't just, have one pencil and move down here, move down here, move down here, get here. Oh, there's my number that's bigger. Because we need to do something with the node that came before. So we're going to use a pair of pointers. We're going to have the node that we're looking at right now, that's what I call this index, and we're going to remember the previous node, which was last index. And we're going to move these in lockstep. And now when we get to the point where this node is bigger than the one we're inserting, we've still got something pointing to the prior node. Because in this case, last index was one less than this index. That's not always going to be the case. So we got to keep a pair of pointers, move them through, so when we get to the node that we're interested in working with, we have something that tells us the previous node. So initially, this is last index, and this is this index. And then as we move down, this becomes last index and this index. And as we move down, this becomes last index and this index. And now we find the 25 we want to insert before. We've got something pointing to the previous node. So someone says, I thought you only needed to store the previous node in case you wanted to be able to move backwards. You actually do want to move backwards in here, right? So we want to insert a 20. Too small, too small. That's the spot that we want to insert before. Well, to insert before that, we need to go back to this node and change its next field. We need this to point to our new node. So in a sense, we are backing up, right? We're going to create a new node. we're going to store a 20 in there. It wants to come before here. Well, we've got to back up one spot and take that previous node and have it point to the 20, and then have that point to the next. All right, so we're moving through the list. We've got last index, this index. We want to insert between last index and this index. All right, so we're going to do this, and this is going to tell you everything you need to know for the rest of CSE222. So here's the whole course. We've got a 15, we've got a 25, we've got a pointer. All right, we're inserting a 20. So we've got to find another spot in memory where we can store this 20. So how do we do that? Well, we're going to go through, we're going to find a spot where the valid flag is 0. We're going to store a 20 there, and we're going to set the valid flag to 1. And we're going to note its index. We're just going to call that new index. So that's a 4. All right, last index is 2, this index is 3, new index is 4. So how do we insert? So new index, that's a data value of 20. All right, watch closely. We want to insert this node between last index and this index. So we need to do two things. We need to change last index to point to new index, and we need to change new index to point to this index. Well, that's exactly 2 lines of C code. So first line, let's adjust last index. So let's suppose this is, our array called LL. Okay, LL bracket last index. Right? That's this node right here. We want to change its next field to refer to new index. So set that equal to new index. That's not pseudocode, that's actual C code. Okay, what does this do? This says my linked list array indexed at last index, right? Last index is 2, so that's this entry right here. Let's change the next field to be equal to new index, which is 4. That statement does this. Right? Done. So this statement is changing this arrow from where it was pointing to this new thing. In memory, it's taking this field in this struct node and changing it from pointing here to pointing to our new node. So now our 15 points to the 20. What's the last thing we have to do? We need the 20 to point to the 25. One more line of code. Linked list, take the element at new index, and let's set its next field to be what? Let's set it to this index. So that's going to take the linked list's data, the struct node at new index, which is a 4, that's this node right here, and we're going to set its next field equal to the value of this index, which is a 3. Well, what does that do? That does that. And we're done. we've inserted our 20. So now we go through our linked list. Once we get to the 15, if we follow that link, it'll take us to 20. If we follow that link, it'll take us to 25. All right, this code is worthless, right? Do not memorize this. Do not look at this when you're writing your code. This is not the point, okay? This is the point. If you understand how we want these arrows to change, and you understand how this picture is stored in this array of struct nodes, you can write this code yourself. That's what you want to be able to do. Once you can do that, you're done with CSE222. Not really, but you know, effectively, right? Once you understand how you want the data structure to be manipulated, and you know how the memory should be modified to cause that change, then you can write the code to make that happen. And it's usually just a few assignment statements. So you're trying to get to the point where you can write these two statements in response to the question, how do I insert a new node? Assuming I've moved through and I found this index and last index, right? That's the goal. That's the whole reason that we're going to be doing all of these programming assignments, is to help you get to the point where you can translate this into memory manipulation and then put down a few lines of C code to cause those memory changes to take place. That's the essence of CSE222. Yeah, so now we can do basket weaving and scuba. Awesome. Okay, so we did not make it all the way through the write-up, but that should be plenty of stuff to get you going. That should be enough for you to write an add function. You can certainly work on your main program, because that's CSE224 details, right? And if you can do this for an add function, I would say doing the search or the print should be pretty straightforward. There's no manipulation of the data structures in there. Delete is the only other function that actually modifies the data structure, and it's easier than search in some way, easier than insert in some ways. There's one more important set of details here which we'll go through on Monday, but basically this business of, you know, I wanted to make a new node, I needed to find a spot where the valid flag was 0. I want you to write a pair of functions to deal with that. I want a function called getNode, which does exactly that. Looks through your array and finds the first entry where valid is 0, right? And then sets it to 1, returns that index. And then release node, which we use when we delete, will go ahead and clear a valid flag. So we'll talk about those on Monday also. But you've got enough information now to get, you know, a good 80 or 90% of this program done over the weekend if you want. So jump into that, right? And we'll talk a lot more about this on Monday. We'll talk about how to test this. But try to develop it in steps, right? Don't just try to write the whole thing and then compile it for the first time. Build it up in steps, right? You've got your init function. Try adding a node and run it in GDB and take a look at your structure, right? Look at what's pointing, what your array looks like, and build it up from there. And once you get 1 or 2 of these things working, the third one becomes really easy, the fourth one becomes much easier, and by the fifth one you're doing it in your sleep. Okay, so it will you know, be some kind of learning curve, and then all of a sudden it gets really good. All right, we are past time, so rock on with that. I will see you in 2:15 if you're in there. Otherwise, have a great weekend, and I will see you on Monday.